This lecture is entitled Thank You Prometheus, and it is our lecture on the relationship between light and atomic structure. It says Prometheus, thief of light, giver of light, bound by the gods, must have been a book, because Prometheus is often seen as the giver of knowledge, and so are books. So the learning goals for this presentation are: number one, that you understand the differences and similarities between each type of electromagnetic radiation. Now, a lot of people think of electromagnetic radiation as just light. Okay, but that's not the case. There are actually 7 total parts, and light is the smallest of all of them. So it's a very, very, very small part of the electromagnetic spectrum. You're supposed to understand the relationship between frequency, wavelength, velocity, and energy. Okay, there's a relationship between all of these variables that we're talking about, with frequency being signified as an F, energy being signified as a capital E, velocity being signified with a lowercase v or sometimes a c, since we're talking about light and light's constant, and wavelength being signified with a Greek letter lambda. And then you're also going to be able to relate the quantized model of light with the Bohr model of the atom. So we start off with the electromagnetic spectrum. This is electromagnetic radiation. All electromagnetic radiation travels at 3 times 10 to the 8th. A lot of times this is referred to as the speed of light. But in actuality, it's the speed of light, radio waves, microwaves, gamma rays, X-rays. The whole electromagnetic spectrum operates at 3.0 times 10 to the 8th meters per second. So that's one of the ways you can tell if something's an electromagnetic wave. It can travel at 3 times 10 to the 8th meters per second in a vacuum. Now, it turns out that it will slow down a little bit when it travels through something like air, water, glass, but this is a hallmark of any electromagnetic radiation, that it travels at this speed. Now, if you notice, the electromagnetic spectrum encompasses several different types of radiation. The first one is this long wavelengths over here is radio waves. And then when you get over here, you have microwaves. Whenever you get over here, right next to light, you have the infrared. This very, very small portion right here of the rainbow represents what we now know as visible light. That's the only thing you can see in terms of the electromagnetic spectrum. Then when we continue on from there, just above visible, we have ultraviolet. Just past that, we have X-rays. And at the very far end, we have something that are called gamma rays. The first one is radio waves. Radio waves have a very, very low frequency. Okay, so they have a very, very, very low frequency. They have a very low energy. And they have a very high wavelength. Now, the primary purpose of a radio is to transfer information somewhere. So what you see here is you have a radio tower, and it generates radio waves that come out. Now, contrary to what a lot of people think, you can't hear a radio wave. Instead, what you have to do is you have to have a device called a radio that takes these radio waves and converts them to sound. You can hear sound, but you cannot hear radio waves. So radio waves are the lowest energy ones that we're talking about here. They're the ones that you shouldn't be concerned with them as far as they're all over the place, because there's no way that they can cause any damage to you because they have such a low energy. Next, we have microwaves. Microwaves have a slightly higher energy and a slightly higher frequency, but they have a slightly smaller wavelength. So you see this relationship that as you increase in energy and frequency, you actually decrease in wavelength. That's going to be really important. So we had radio, and then now we're at micro. The primary purpose of microwaves is to heat food, because what happens is it actually sends microwaves that resonate at the same frequency as water. So what happens is it causes the water molecules to heat up by moving faster and faster and faster. Another purpose of microwaves is the fact that it's actually used to communicate. That's the frequency that cell phones operate at. If you were to take your cell phone and remove the battery, generally you see something that it operates at so many gigahertz or something along those lines. That's generally the frequency that cell phones will operate at. Infrared radiation is the next type of radiation. Infrared radiation is also known as heat. Okay, so heat is slightly higher in energy, slightly higher in frequency, and slightly smaller in wavelength. So you see that same pattern. We have radio, micro, and infrared. So as we go this way, we're increasing in energy, we're increasing in frequency, and we're decreasing in wavelength. Now, infrared radiation is heat, so anything that you can think of as heat is an example of infrared radiation. one of the primary things that you can see is the sun actually heats the earth, and that's infrared rays. But you can also see in the dark using something called infrared goggles. Most of the time it's called night vision goggles, but you can use infrared goggles to see something at night. Visible light. This is the smallest part of the electromagnetic spectrum, and it's anything that you can see. Okay, it's considered to be medium frequency, medium energy, medium wavelength, and it's the only part of the electromagnetic spectrum that you can actually see. So you see radio, micro, infrared, and then right in the middle we have visible light. And like we said, visible light is really, really, really small. Now, uses for visible light are all of obviously seeing. So if you can use a telescope, glasses, a microscope, anything that you can actually see with would be a use for visible light. Next, we go to ultraviolet. Okay, ultraviolet is slightly higher in frequency and energy than visible light, because remember we had visible light, UV, radio, micro, infrared, and so as we move this way, remember we're going up in energy. So we have a high energy, we have a high frequency, and we have a low wavelength. Now, these can actually be used to sterilize medical instruments. So if I have, let's say, a scalpel that I used in surgery, they will wash that scalpel, but then also what they do is they subject it to UV radiation. And the reason why they do that is because if you subject something to UV radiation, it can kill all the bacteria that are on the top of that particular scalpel, things that you couldn't even get if you washed it really well. So it can be used to sterilize medical instruments or hands or things like that whenever you're going to work in a high-level research facility or something like that. But it's also the primary causes of sunburn. Okay, whenever the sun has UV radiation that hits the skin, okay, UV radiation can actually penetrate the first couple of layers of skin. It's really the first one that can do that. Okay, it can't go very deep into the skin, but it can penetrate the first couple of layers. And because of that, it can actually cause a sunburn. It also causes you to tan as well. Next, we have X-rays. X-rays are even higher in frequency and energy. Okay, we're starting to talk about the first things that actually penetrate all layers of skin. So it goes through all layers of skin. And it has really, really high energy and it has really, really low wavelength. So once again, if we look at our pattern, radio, micro, infrared, visible light, UV, and then now we're at X-ray. So we're starting to get things that are really, really, really high in energy. Now, X-rays are obviously used to take a look at bones because they actually penetrate the skin but cannot penetrate the bone. So what they do is they put a film behind you and then they shoot the X-rays at you, and whatever doesn't get through, you kind of get this solid white pattern saying, okay, that's solid because X-rays didn't get through. Where it's these little gaps right here, that could indicate a break because it's saying, hey, little X-rays could get through there, indicating that there's something there. Now, your skull is notoriously difficult. It's very hard to get an X-ray off of your skull because your skull is very good at stopping electromagnetic radiation from coming to your brain. Your brain needs to be kept kind of safe from most forms of electromagnetic radiation, so it's developed a skull that can actually keep most of it out. Gamma rays are the highest in energy and the highest in frequency. They are the smallest in wavelength. Now, gamma rays represent the extremes. So remember we have radio, micro, infrared, and we had visible in the middle. And then now we have UV, X, and gamma. Okay, a lot of times you'll see gamma abbreviated with this. This right here is the Greek letter for gamma. It's kind of like a fish that's facing downward. That right there represents a gamma ray. It is used primarily in radiation therapy to treat cancer. So it's not chemotherapy. This would actually be radiation therapy. What they do is they have a cancer cell, and what they're trying to do is they're trying to target this specific cancer cell without getting any of the surrounding healthy tissue. So this is healthy. And so what they want to do is they want to use a very, very, very high level of energy, but a very, very low wavelength so they can target this specific area and cut out all the cancer cells but leave most of the healthy tissue intact. Example A1, it says the sun has an average coronal temperature of 300 million Kelvin. Speculate on the primary type of radiation produced by a theoretical star with a coronal temperature of 100 million. Justify your answer using the clear method. Okay, so remember when we're talking about the clear method, we need a conclusion, we need evidence, and we need reasoning. So now, the evidence is going to be pretty simple in this case. You have 3 million and 100 million. So what this is indicating is the fact that there is more energy in the star. So you have a higher degree of energy. Now if you look, it says that our star emits primarily visible radiation. So you've got our star that's emitting primarily visible radiation, and then you have another star that's got a lot more energy in it, and you want to know what its primary radiation would be. So we've got our evidence, we've got our kind of an idea on reasoning. So let's go ahead and say our conclusion. The conclusion would be anything greater than visible light. So you could say UV, you could say X, and you could say gamma, and all of those would be valid answers. And the evidence would be because the star is over 30 times hotter than our star, and therefore it has more energy. When it has more energy, it's going to shift up the EM spectrum. Now there's no way of knowing for sure what it would be, but we know it would shift up the EM spectrum to one of these. A cell phone frequency is very similar to the frequency that causes a water to heat up in a microwave. Should you be concerned about a cell phone close to your head, justify your answer using the clear method. Okay, so once again, we're looking at a conclusion, we're looking at evidence, and we're looking at a reasoning. The real clear answer is no, that you shouldn't be concerned with it. So now we just need to find some sort of evidence and reasoning to back it up. And the evidence is that it has a similar frequency to water. Okay, so we're talking about similar frequency, which also means it is a low frequency. Relatively speaking, it is a low frequency and it has low energy. Now when we look at reasoning, our reasoning that we're talking about would say, okay, well if something has low frequency and low energy, it cannot penetrate the skull. Remember, even X-rays have a hard time penetrating the skull. So penetrate skull. Alright, so this is example A3. It says develop an acronym to help you remember the order of frequency, wavelength, or energy. So you have this RMIVUXG. You need to be able to remember those things in order, and so it's kind of helpful to sometimes generate an acronym. I've heard everything from Red Martians to Ricky Martin to whatever you want to come up with, but some sort of acronym that helps you remember that, because you do need to know that order for frequency, energy, or in reverse for wavelength. The EM equation. So the electromagnetic equation comes with this. This is the formula. It says C equals lambda F. This C stands for the speed of light. Okay, it's represented by C and it's measured in meters per second. The definition is how fast all EM radiation travels in a vacuum. So anytime you see C, C is 3.0 times 10 to the 8th meters per second. Always. That's what it is. Now, this lambda term right here stands for the wavelength. And what that is that is the distance between identical parts of a wave. So you have a peak of a wave and the peak of a wave. That distance between those two represents wavelength. And then finally you have frequency, and frequency is the number of waves per second. And so, for example, you could have a wave like this, or you could have a wave like this, where it's real bunched up together. This would have a much higher frequency because more waves would pass every second. So all of those go into this formula C equals lambda F, which is kind of one of our first calculations that we're going to be really doing in this class. So there's a very specific way that we're going to solve problems in this class that you should definitely follow. Example B1, it says an X-ray maintains the same frequency of 3.0 times 10 to the 17th hertz, regardless of the medium that it travels in. Okay, X-rays travel at 1 times 10 to the 8th meters per second in soft tissue. What is the difference in wavelength for the X-ray in tissue and in a vacuum? So this is a two-step question. So this is one of the harder questions that you'll see. This is an example of a higher level question on a test, not just one of the easier ones. So let's take a look at what we've got. You always want to kind of record what numbers you're given off the bat. So the first thing you want to realize is that you're going to have to do this calculation twice. You're going to have to do it for in the skin, and you're also going to have to do it for in a vacuum. So we divide it in half and we say, okay, well, what do we know about a skin and the vacuum? Well, when you look at this, it says it maintains the same frequency regardless of the medium it travels in. So what we can say is we can say for both of these, frequency is 3 times 10 to the 17th. And 3 times 10 to the 17th hertz. Now, what else do we know? If you come back here, it says X-rays travel at 1 times 10 to the 8th in soft tissue. So we know that in the skin, the velocity is going to be 1 times 10 to the 8th meters per second. And we know in a vacuum that light always travels at 3 times 10 to the 8th meters per second. So if you look at this, we have enough information that we're going to use our formula right here. And our formula is going to be C equals lambda F. Now I'm going to do it twice, and I'm going to do it once with the vacuum and then switch colors and do it once with the skin. But what you see is, on this side you'd say 3 times 10 to the 8th equals, you'd have lambda, which you don't know, and then you'd have 3 times 10 to the 17th. You divide both sides by 3 times 10 to the 17th, divide by 3 times 10 to the 17th, and you would get your answer. Now, we do it on the other side, and we would say 1 times 10 to the 8th equals lambda times the frequency, which is still 3 times 10 to the 17th. Divide both sides by 3 times 10 to the 17th. And then when you do that, you would get your answer as lambda. So you have two wavelengths right here, one for when it travels in a vacuum and one for when it travels in the skin. So when we do the calculations, we get 3 times 10 to the 8th divided by 3 times 10 to the 7th, or excuse me, 1 times 10 to the 8th divided by 3 times 10 to the 17th, and you would get 3.33 times 10 to the negative 10th. On the other side, whenever you do your calculation, you would do 3 times 10 to the 8th divided by 3 times 10 to the 17th, and you would get 1 times 10 to the negative 9th. So you've got these two values. You've got the wavelength of the vacuum, you've got the wavelength of the skin. What it's actually asking you is what is the difference in wavelength? So the difference would be, I would have to take these two and subtract. Now realize that this is the larger number because of this exponent value. A lot of people say, oh, well, 3 is larger because it's 3 and this is 1. Remember, you always look at the exponent value, not just the numbers in front. So when you do 1 times 10 to the negative 9th minus 3.33 times 10 to the negative 10th, you get something like 6.67 times 10 to the negative 10th. That is your final answer. Example B2, it says, what is the wavelength of red light in nanometers? And it gives you a frequency. So you should be able to take this and you should be able to say, okay, I know C equals lambda F. This right here is my F value. I always know what C is, and so you should be able to plug those into an equation without any other help, and you should be able to get the final answer, which is 7.5 times 10 to the 7th. But remember, that's in meters, so negative 7th, and it asks for it in nanometers. So it's going to be up to you to convert that value correctly. You've got to be able to convert between nanometers and meters. This example B3, it says the sun emits all different forms of EM radiation. Which segment of the EM spectrum will reach the Earth first? Remember that all segments of the EM spectrum travel at the speed of light. So they all travel there. None of them get there first. They all get there at the exact same time. So, what is light? So this is kind of an interesting question because we have some different evidence to take a look at what light is. The first one is light is a wave. What we have is called Young's experiment, so often called Young's double slit experiment. And what it is just evidence that light acts as a wave. So you have a light source that generates light, and whenever this light comes, it hits these two slits. Light will then diffract, which means it will generate a new light source here and a new light source here. Whenever you do that, these two light waves are identical because they came from the same source, and they have the opportunity to what's called interfere with one another. So whenever they interfere with one another, this wave and this wave can combine to make something new. And you can see that in the pattern on the wall. You have a really bright spot, but then you have these dark spots right here. Normally, if you think about it, if you take two flashlights and shine them on the wall, it just becomes a brighter spot. But in this case, you have these bright spots and then you have these alternating dark spots. What that means is that the waves are actually interfering with one another. So whenever you have a bright spot, you've got two waves that match up, and therefore they get bigger. Whenever you have these dark spots, what happens is you have a wave, and then you have a wave that's the exact opposite. And when you add those together, they cancel each other out, and you get a dark spot. So what this is evidence that light's actually a wave. But then when you contrast that with this, light is a particle. This is something called the photoelectric effect. And this is what Einstein won a Nobel Prize for in 1905. The photoelectric effect says that light's a particle. And the idea is this. If you were to take a red light and shine it on this, nothing would happen. If you were to take a green light and shine it on there, nothing would happen. But if you were to take a violet light, like it shows here, and shine it on this, then all of a sudden these electrons, these particles get ejected and move across. And that doesn't make a lot of sense if you think of light as a wave. Because remember, red light is just like this, right? So eventually you'd have enough energy that would keep going in and keep going in and keep going in that it would eventually kick off an electron. But if you think of light as a particle, so like a pool ball or a billiard ball. So here's my red light, and here's an electron that wants to get knocked off. Well, if you've ever played pool, if you just barely tap it so these just barely touch, this one's not going to go anywhere. Okay, in fact, neither one of them are going to go anywhere. They're just going to stop. But if you were to take this and change it to violet, that would give it more energy, and you could really, 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 really strike the ball. All of a sudden, this electron is going to fly off this way, even though this one would come to a stop. So this right here is evidence that light's a particle. So we have one experiment that says, yeah, light's a wave, and we have another experiment that says, yeah, light's a particle. So what we do is we say, light exhibits what we call wave-particle duality. And you can see this in this picture. So you have a particle, which is signified by the ball, and then a wave inside of it. So this is wave-particle duality. So what you do is you pick the easiest form for the experiment that you're trying to perform. So let's say you're trying to perform something that uses interference. Then you would say light's a wave. If you're trying to say something where light needs to hit something, well, then light's a particle. It turns out that it's really both, though. And you may learn later that actually everything exhibits wave-particle duality. So, what is light again? Or how is light produced in this case? So, light or EM radiation is produced when you have an electron that falls down. So we talked about this earlier when we talked about models of the atom. You have the nucleus and you have these things called orbits. Now, electrons want to be in as low as an orbit as possible. They want to be as close to that nucleus as possible because opposites attract, right? You've got negative electrons and they're attracted to the positive nucleus. Sometimes, though, this electron will jump up to a higher level. So here's the electron. The electron doesn't want to be there. So what it does is it actually falls back down. But the conservation of energy says you can't just lower the energy of an electron without doing something. You can't destroy that energy. So it turns out that whenever this electron falls back down, it emits a photon. And a photon is known as a particle of light. So what you have right there is you've got a particle of light being ejected. Well, that means some very specific things that we talked about when we talked about the Bohr model of the atom. It says that EM radiation can only have a certain amount of energy called a quanta. Yeah, because if you have this orbital that's number 2 and this orbital that's number 1, you can only have an energy that's the difference between these two, which is why you had the certain lines on the Bohr model of the emission lines. So you have this right here and this right here. This has to be the energy of the photon. You can't have half of that energy or a third of that energy. It's got to be that. So that's the quanta value. Now, this makes every atom unique because the relationship between these two orbitals is different for every atom. That's why every atom emits a different color. So the energy of radiation can actually be determined using this equation right here. You see E equals HF. E stands for energy. Energy is measured in joules, and we'll study it a little bit later this year, but mostly you'll learn about it in physics. So energy in joules, and then we have F right here, which stands for frequency. Frequency is measured in hertz, and we've already talked about that. The new thing really that's here is this H value. This H value is called Planck's constant. And Planck's constant has a value of 6.626 times 10 to the negative 34th. It's a very, 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 very small value, but it's a constant. So just like when we said C equals lambda F, you always knew C. When you do E equals HF, you always know H. So it makes it a little bit easier. If you know one of the other numbers, you can solve for the next one. Example C1, it says how many red photons would it take to equal the energy of 10,000 violet photons? And then it gives you some numbers that are associated with that. So remember, we want to write out all our information. So the first thing we want to do is what information is given to us. We're going to draw a line down the page that kind of separates those two. And we're going to start off with red and violet. And we're going to separate it into two different things. So now, what information is given to us? Well, if you look, for violet, you're given that there are 10,000 violet photons, and you're given the wavelength of those photons. So I'm given that there are N, which is 10,000 photons. And you're also given the fact that the wavelength of those is 430 nanometers. Now, the first thing that you should realize is this nanometers isn't going to work. We always do our calculations in meters. So you're going to end up dividing by a billion to get to meters. And so this is going to be 4.3 times 10 to the negative 7th meters. So now I have the wavelength. Okay, now let's look at what we have for red. If you look for red, I have the frequency of the red light. The frequency of the red light was 4 times 10 to the 14th. And what I eventually want to know is the number of photons that equal that. So if we look back at the problem, how many red photons would it take to equal the energy? So that's going to be our key here. So I can do E equals HF and E equals HF. But remember, the E equals HF formula is for one photon. Now I'm going to say I've got more than one photon. So I've got to add this N term here, multiply what each photon is by the number of photons that I have. If you look, this formula is the same on both sides, but the frequency for red light is going to be different, the number for red light is going to be different, the frequency for violet light is going to be different, the number for violet light is going to be different. But the energies are going to equal each other. So what I can do is I can say NHF equals NHF. Now, the number for red and violet light are going to be different. Planck's constant is a constant. It's the same on both sides, so it will cancel out. So now you have frequency. Frequency is going to be different on both sides. So now we can go ahead and plug in our numbers. What I have for red light is I have N times 4 times 10 to the 14th equals, and then on the other side for violet, I have 10,000. Oh, and I don't have frequency. But what I do know is I could do the formula C equals lambda F. You have C, which is 3 times 10 to the 8th. And then you have lambda, which is 4.3 times 10 to the negative 7th. And then you can actually go ahead and figure out what the frequency is. I'm going to leave it in the form that we talk about here. This rearranged version where you have frequency equals C over lambda. So you have frequency equals 3 times 10 to the 8th divided by 4.3 times 10 to the negative 7th. So now you've got a number on one side because you can multiply all this out. So in order to figure out what n is, all you've got to do is get rid of this 4 times 10 to the 14th. If you divide both sides by 4 times 10 to the 14th, now you've got your answer. Before we do the math, you should be able to say, should it be more than 10,000 or less than 10,000? So think about which one of those has more energy, violet light or red light. And you should know that violet light has more energy. So since it has more energy, you should be able to say that there should be more red photons because they have lower energy than violet light because they have more energy, if they're going to equal the same value. So whenever you do this, you should end up getting an answer somewhere close to 17,500 photons. It's actually like 17,440 photons. But that should actually be, we should have written this in red because this is red photons, not violet. What is the total energy of 1,500 yellow photons if the wavelength is 580 nanometers? So we look at what information we're given. We're looking for the total energy. We have the number of yellow photons. We have the wavelength of those photons as being 580 nanometers, which converted would give you 5.8 times 10 to the negative 7th meters. And then you are trying to figure out what the energy is. In order to figure out the energy, remember the formula is E equals HF. But we don't have F in this case, so what we can do is we can use our other formula, C equals lambda F. We divide both sides by lambda, and you get frequency equals C over lambda, or E equals HC over lambda. You should be able to take the numbers that you have now, and people say, well, where's the n go? Remember, this is for one photon. In order to make it for multiple photons, you have to multiply it by n. So now if you look, you have n, you have C, which is a constant, you have H, which is a constant, and then you have this, which is your lambda value. So you should be able to plug those in and get the energy. The final one says sketch the shape of the energy versus frequency graph. It says what is the relationship between these variables. So you have E equals HF. Anytime you're graphing something from an equation, it actually is really easy. You assign them to different variables. So this energy is the Y value because it's going to depend on the frequency. Frequency doesn't depend on energy. Energy depends on frequency. And this is going to be the X value. Now, those are the two variables you're graphing, so everything else goes away. So you take this and you say E equals HF. That's not in the graph. So you would say E equals F as far as the graph is concerned. You switch them out and you say Y equals X. Y equals X is your straight line graph. So you have a straight line graph right here. And then you realize that if you have a straight line graph, so Y equals X, the slope is determined by this value right here, which on our graph was H.